Hello dear friends, welcome to Unacademy NEET English YouTube channel. I am Kailash Sharma and today I am going to cover three very important topics of the thermal physics, and those are heat transfer, thermal expansion and the calorimetry. They are very important for NEET as well as for JEE Main. So students preparing for the NEET 2024 must be benefited by this session because one or two questions are asked from this part. I hope you all are already excited for the session. So we start the session. Before the start, do not forget to like, share and subscribe the YouTube channel where you are getting one of the best content by the top educators of Unacademy on this channel only. I am teaching you the 11th part of the physics where I have already covered the units and dimension, error and measurement in one session. Other session was on a function, which is the basic mathematics part, and the third session was on the vector and calculus. Fourth session I have conducted on the KTG and thermodynamics. So KTG and thermodynamics I have already taught on this channel, and now with this session, today's session, we are going to cover the remaining three topics of the thermal physics, and after that our thermal physics will be completed on this channel. So we will start with the heat transfer. I'll cover the theory as well as the questions. So before we start, please don't forget to like the session. I want, let's cross the 100 likes mark in next 2-3-4 minutes. Okay, thank you. So today, our NEET Endgame batch, which is a crash course for the NEET 2024, has already started. Most of you have already joined. There is an offer going on for a limited period. So if anyone out of you is interested in that crash course, where we are going to cover the entire syllabus of the physics, chemistry and the biology, and this course is beneficial for the NEET 2024 because it is dedicated for them only. The link in the description is given for the batch. So go through that link and just check out what we are offering in that batch. This will definitely benefit you. Okay, so we start the class. Good evening, good evening, good evening everyone, good evening. I can see so many messages of good evening. Okay, good evening. So behind me you can see so many images. These images are one of the beautiful images. Here you can see the shining sun, thermometer, railway track, and that is called the calorimeter. These all the images are related to today's topics, which we are going to cover in the next 4 to 5 hours. So here we will start with the heat transfer, then we will move to the thermal expansion, and then the last topic will be the calorimetry. So we start the class. Wait 1 minute. Let me take the slide changer. So we start the heat transfer with the, so first topic we are going to cover is the heat transfer. So these are very beautiful slides you can see here. So first word, which is the, so basically I am going to tell you a few things about before we start the topic. Thermal physics has total 5 parts. First one is the calorimetry, thermal expansion, heat transfer. These 3 parts are separate from KTG and thermodynamics. These KTG and thermodynamics are the last 2 parts of the thermal physics. So complete thermal physics consists of these 5 parts. 2 we have already completed, KTG and thermodynamics I have already taught on this channel only. Remaining 3, which are the heat transfer, calorimetry and the thermal expansion, we are going to study in this class. So thermal physics, there is a possibility of, out of 50 questions, there are 50 questions in physics. Out of those 50 questions, 45 we have to attempt. So out of those 50 questions, they can ask up to 3 to 4 questions from thermal physics part. So all these 5 parts in 2 classes will definitely help you in scoring at least 16 to 20 marks. So these are high weightage topic. That's why I am covering them. So this see one thing. This number varies from year to year. I'm not saying every year there will be at least 4 to 5 questions asked from this part. Sometimes it can go below below up to 2 questions only from this part, and sometimes it can go more than that. So we have to be prepared. At least 4 questions on an average you can consider from all these 5 topics, and in 2 classes 16 marks you are going to prepare for your NEET 2024. So that's why these topics are very, very important. You have to just spend the 5 hours on the KTG and Thermodynamics class and 4 to 5 hours on these 3 topics class. So equally, they are equally important. That's why I'm saying properly watch the session till the end, so that you make sure that you are able to score those 16 marks. And after watching these sessions, the way I cover all the concept in the detail, you will definitely be able to do this. So okay, so heat transfer is our first topic, and I was telling why we study this, like what is the difference between that. We have already covered KTG and thermodynamics, and these 3 topics today we are going to cover. Today we are mostly going to talk about the solids and the liquids. And in previous session where I covered the other part of the thermal physics, that was the KTG and thermodynamics, there we mostly talked about the gases. In kinetic theory of gases, we studied, we define a gas, we talked about the parameters of the gas, and then in thermodynamics, we talked about the processes on the gas. But in these 3 topics, we mainly talk about the solids and the liquids. So heat given to solids, liquids, or processes on the solids and liquid we will talk about. So that's why we keep them separate. KTG and thermodynamics is more about the gases, and these 3 topics are more about the solids and liquids. That's why we have to conduct 2 sessions to complete the thermal physics. So some people teach this first and then KTG and thermodynamics. There is that hardly matters. KTG and thermodynamics is equally important. So that's why I covered that first. Okay, so now we start the session. So are you ready for the class? Ready for the class? So first we will talk about the heat energy. We are going to start the topic with the heat transfer. So first we will talk about what is heat. The word heat we are using for very long time. When the session started, I just read the first word was the heat transfer. So what is heat? What is the heat? You all have felt it. Like you all have sometimes in life, or you say every day in your life, you encounter with the heat. What is heat? So here you can see an image where there is a fire and a person is next to the fire. So it is taking heat from the fire. Like maybe this is the image of winters. So he needed heat to stay alive. So he's sitting next to the fire and taking heat from the fire. So what is this heat energy? How does it flow? What is heat transfer? So before we start, let us understand what is heat energy. So there is the definition of the heat energy. Heat is also a form of energy. The energy that flows due to the temperature difference between the 2 systems is called the heat or heat energy. So heat is the energy that flows due to the temperature difference between the 2 systems. So there are 2 systems. They have the temperature difference. Then the one at higher temperature will transfer heat to the one at the lower temperature. So if there are 2 systems, one higher temperature system will transfer the energy to the system at the lower temperature, and this energy that flows due to the temperature difference is called the heat energy. So is this clear to all of you? Heat is also a form of an energy, and the energy that flows due to the temperature difference is called the heat energy. See, temperature is the term which let us feel that a surface, a body is warm, hot or cold. But the energy that is flowing due to temperature difference is called the heat energy. So when you touch a hot surface, your your skin starts, uh, uh, your skin feel burned. Why so? So when you touch a hot surface, that hot surface is at a higher temperature and your skin is at a lower temperature. So when you touch a hot surface, there is a heat flow from that hot surface to your skin. That's why your skin is burning, like, or it feels like burn. So that is also, so that surface is hot because its temperature is higher as compared to your hand. That's why your hand is feeling that that surface is hot, because from that surface heat is flowing to your hand. So heat flows from higher temperature system to lower temperature. And if you touch a cold surface and your hand has higher temperature than the surface, then heat will flow from your hand to that surface and you start feeling cold, because there is a loss of heat on your on the part of your skin which is touching the surface. So cold or hot is related to the temperature, and when a hot body is in contact with the cold body, then there is a flow of energy from the hot body to the one at the lower temperature, to the body one at the lower temperature, and that flow of energy is called the heat energy. So is the heat energy term is clear to you, and the difference between temperature and heat is clear to you? So the both difference between the temperature and the heat is clear. So hot and cold are different thing, and heat is a different thing. Clear? So energy that flows due to the temperature difference between the two systems is called the heat energy, or this energy flows from the temperature from the system at higher temperature to the one at the lower temperature. So heat energy flows from higher temperature to lower temperature system. And because of temperature, we have this idea that this body is hot or this body is cold. So if a body has higher temperature, that is hot, lower temperature cold. So that is relative term basically, na? Hot or cold is a relative term. You are touching a surface and its temperature is greater than your hand or your skin, then you will feel that that surface is hot, because there will be heat transfer from that surface to your skin. So your skin is getting heat, so it will feel warm there, and surface is at lower temperature than your skin will lose heat when you touch that surface, and you start losing heat, then you will feel cold. Flow of energy due to temperature difference is the heat energy, and heat flows from higher temperature to lower temperature. This first line is clear to all of you. The SI unit of the heat is joule. We measure heat in joule as well, but the most popular unit is calorie. Mostly it is measured in calories. So heat is measured in calorie. 1 calorie, there is a definition of the calorie also I have written, so that once in a JEE main exam, they directly ask this definition, and in this definition there is a data. They change this data in 4 options. So one who has never gone through this type of definition of the calorie were not able to answer that question. So 1 calorie is the amount of heat. You have the unit of the heat is calorie. So what is 1 calorie means? Like 1 calorie, how much heat is 1 calorie? So there is definition of that as well. 1 calorie is the amount of heat required at a pressure of 1 atmosphere to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius is called the 1 calorie of the heat. So 1 calorie of heat is the heat energy that is required at a pressure of 1 atm to raise the temperature of water of 1 gram from 14.5 degrees Celsius to 15.5 degrees Celsius is called the 1 calorie. Basically, to raise the temperature of 1 gram of water from 1 degree Celsius, the amount of heat given is equal to 1 calorie. But this unit 1 calorie is defined for 14.5 degrees Celsius to 15.5 degrees Celsius. But in general also, whenever you are changing the temperature of 1 gram of water by 1 degree Celsius, you need to supply 1 calorie of the heat to the water. So it is, this data is important. This data is important. They might give you 4 options. One is saying 13.5 to 14.5, another saying 14.5 to 15.5, some other option saying 15.5 to 16.5. So what is 1 calorie? 1 calorie, you have to remember this number. 14.5 to 15.5 degrees Celsius, you are changing the temperature of 1 gram of water. The amount of heat needed to do so is equal to 1 calorie. 1 calorie definition is clear to everyone. 1 calorie is clear to everyone. Okay. So heat energy we have covered. Heat energy. What is heat energy? How does heat is transferred from the system at higher temperature to one at the lower temperature? How do we transfer the heat? So there are 3 modes of heat transfer, and those 3 modes are, first one is the conduction of the heat. The modes of heat transfer. First one is the conduction of the heat. So here you can see a beautiful image. Have you ever visited the shop of the blacksmith? Like, there is an iron rod. He is holding this rod, the other end of the rod with a tool, and this end of the rod is in the fire. So this end I can see this is hot, but why he is not holding this end with the hand? Because there is a heat flow inside this rod, and this end of the rod also gets heat, and that's why the temperature of this end also rises. So this type of heat flow inside this rod is due to the conduction. In our home as well, we have some kitchen appliances which have handle made of the insulating material. That is because of conduction, the handle which is made of the metal also gets heated. So to avoid burning from that handle, we generally use the insulated material on the handle. The same process we can understand from here. Like this rod, the other end which is not in the fire, which is not in the contact of this fire, is also gets heated because of the conduction. There is a heat flow from this end to that end. So this type of phenomena, this process is, this mode of heat transfer is called the conduction of the heat. So what is the definition of the conduction? I have written down the definition of the conduction as well. In conduction, heat transfer takes place due to the molecular collision without net mass movement. So basically, from this end to that end, the heat is being transferred during the molecular collision. The material is not going from here to there. This material is not moving. There is no net mass movement, but the heat is moving from this end to that end of the rod by during the molecular collision. So there are molecules and they are colliding with each other. And they are passing heat from the end which is at the higher temperature to the one at the lower temperature. So heat is being transferred during the molecular collision between the molecular collisions. So where the molecules at the higher temperature are transferring heat to the one at the lower temperature, that's why the other end of the rod is also gets heated. Okay, so this is the way the conduction occur. So conduction, which is the first mode of the heat transfer. So in the conduction, the heat transfer takes place due to the molecular collision without net mass movement. So suppose this is the rod, and in this rod we are maintaining the temperature of this end T1 greater than T2. We are heating this end. So when we are heating this end, these are the molecules which are at the higher temperature. These molecules will transfer the heat energy to the molecules which are at the lower temperature. So molecules having higher vibrational kinetic energy. So when you heat one end of the rod, the molecules of that end will have higher vibrational kinetic energy. So when you increase the temperature, these molecules will have higher vibrational kinetic energy as compared to the other end which is at the lower temperature. So the molecules having the higher vibrational kinetic energy transfer the thermal energy to the one at the lower temperature during the collision. So these molecules which are having higher vibrational kinetic energy will collide with the neighboring molecule which is at the lower temperature or having lower vibrational kinetic energy, and during that collision these molecules will transfer heat to those molecules, and again when they attain the energy, they get the energy, they also their vibrational kinetic energy will increase, and again they will transfer heat to the neighboring molecule, and this process keeps on going, and the heat is being transferred from this side to this side during the molecular collision. So the end which is at lower temperature will also be heated, and you are heating this end only. Okay, so let's say let me make, okay, so you are heating this end, that other end is getting heated because of there is a heat flow inside this rod. So molecules having the higher vibrational kinetic energy transfer the thermal energy to the one at the lower temperature during the collision. This conduction, the heat transfer through the conduction occurs in solid, liquid and gases, all three. But main mode of heat transfer in the solid is the conduction. So in solids, main mode of heat transfer is the conduction. So conduction is the main mode of heat transfer in the solids. So are these all 3 points clear to everyone? How does conduction takes place? How does heat flow takes place during the conduction? Yes, in solids it is the main mode of heat transfer. So solids, the main mode of heat transfer in the solid is the conduction. Okay, so now we are going to do the we are going to measure the amount of heat which is being transferred from the system at higher temperature to one at the lower temperature. So we are going to talk about the heat flow rate. So this heat current is the heat flow rate. Heat current through the uniform rod. So we are going to talk about heat, the rate at which heat is flowing through the uniform rod. So here I can see a system at T1 temperature. T1 is greater than T2. Okay, so this is at the higher temperature. System at higher temperature, and this system is at a lower temperature. This system is at lower temperature. So system at lower temperature, system at higher temperature. They are connected by a rod, and the temperature of rod is something else. It is different from these two. Okay, this rod, let's say, suppose this is the rod, and I put that rod between these two systems. One is at the higher temperature. Let's say there is a fire and there is a ice. The temperature of here is say 100 degrees Celsius or 200 degrees Celsius, and there you are keeping ice in this container. Temperature is 0 degrees Celsius. Let's call it like that. You connected both the system with the rod. There is no other way of heat being transferred from this system to that system. We are not considering that some energy, the warmness it will feel from here. No, this is a closed container. Inside temperature is T1. This is the closed container, the inside temperature is T2, and you have connected both the container with the rod which is at some different temperature. What will happen? So when rod is in contact with this higher temperature system, these molecule will start getting energy from here, because here in contact the molecules of this system are vibrating at a higher energy. They will transfer some energy to the molecules of the rod. These molecules will start getting energy. So the temperature of this end will start increasing, and you can see that here this part is shown, the higher temperature part is shown with red. So there will be redness in this rod. So temperature will be higher at this end. This end of the rod is in contact with this, let's call it ice water mixture, or ice which is kept at 0 degrees Celsius. So this end will also change its temperature. So let's say, suppose this rod was at 27 degrees Celsius at room temperature. You put this rod between these two systems. So this end of the rod was at 27 degrees Celsius, but there is ice at 0 degrees Celsius. So this end will start losing energy. The temperature of this end will become close to the temperature of this system. So that's why this end of the rod is blue, this end of the rod is red. So there will be temperature which will fall while moving from this end to that end of the rod. This end will be at the highest temperature, and this end will be at the lowest temperature. Okay, so there will be temperature gradient, matlab temperature will be decreasing when we move from this end to that end. Let's say at any distance x, we call the temperature is T. So when we move dx further, the temperature becomes T minus ka dt. The temperature will fall here. It will fall by dt. The temperature will reduce by dt. And this rate at which temperature is reducing is called the temperature gradient. Are you able to understand this? That the temperature of this end will be highest, the temperature of this end will be lowest, and will be equal to T2, and the temperature of this end will be equal to T1. And there will be decrease in the temperature while going from higher temperature to lower temperature system. So there will be temperature gradient. Now see, there is continuously flow of the heat from this side to this side. From the system at higher temperature to lower temperature, there will be flow of the heat. Heat is continuously flowing from this side to that side. There is a particular state which is called the steady state. In that state, this temperature of the rod stop varying. Say, you can see here, initially the rod was at some different temperature. At every point of rod has changed its temperature. That duration when the temperature of the each point of the rod are changing, that is called the unsteady state. But once the temperature has stopped changing, now whatever heat is coming, entering from this end is exiting from the other end, that state is called the steady state. So there is a continuous flow of the heat from this system to that system. So temperature gradient in the steady state, we will talk about steady state again. In steady state, temperature gradient is defined as minus dt divided by dx. So temperature gradient is defined like this, minus dt divided by dx. This is called the temperature gradient. There will be continuous fall of the temperature. Now you will say, sir, why there is a continuous fall of the temperature? Why are we saying that there will be continuously temperature will be decreasing? See, when you are talking about this element is getting heat from this element, okay? This one is transferring heat to this. So the temperature of this element must be greater than this. Only then it can transfer the heat, because heat transfer takes place due to the temperature difference. So the temperature of this small element will always be higher than this. Same condition will hold for the other one. The temperature of this element must be higher than the temperature of the element here. Only then it can transfer heat. So there is a continuously transfer of the heat. Every element on the left side will have temperature greater than the element on the right side. Only then there can be a heat flow from the left side to right side. Is this clear to everyone? How this heat flow is possible from this side to this side? Because this element will keep its temperature greater than this element. Only then this element can transfer heat. So that's why there will be a continuous drop in the temperature when we move from high temperature body to the lower temperature body. And that decrement in the temperature with x is called the temperature gradient. Okay. There are two types of system. One, lagged system. This is very important. Most of the time people does not teach this. Lagged system. What is the lagged system? Lagged system is a system where you have insulated this rod. There is an insulating layer on this part of the rod. So heat is only entering from here, leaving at the other end. And there is an insulation, there is no heat flow in this side. So when there is a lagged rod, insulating rod, heat cannot exit from here to the surrounding. In that case, this minus ka dt divided by dx is equal to T1 minus T2 divided by L, then in that case the temperature gradient will be constant and the drop of temperature will be like this only. So this is X, this is temperature, here T1, here T2, and temperature will fall like this. Like this. This is X equal to L and temperature will become T2 from T1. Temperature gradient will be like this. So temperature gradient minus ka dt divided by dx will be constant if there is a lagged system. Second system is called the unlagged. In unlagged system, minus dt by dx cannot be written like this. Unlagged system where heat might escape from this part as well. So these systems are called the unlagged system. There is no insulating layer on this rod, and in this kind of system the temperature fall like this, and they might simply ask this graph. This graph is very important. They will not ask a numerical on this. They will simply ask this graph, which is the for the unlagged rod, which is the temperature variation curve. So this is other end T2, this is T1. So there will be curve like this, and this is very important curve, okay, for X equal to L. This is for the unlagged system and this is for the lagged system. Temperature gradient is a very important term in the heat transfer. Temperature gradient is a very important term in the heat transfer. So I'm going to again explain all these things here again. So let's talk one more time. See, heat is the energy which flows due to the temperature difference between the two systems. The system at the higher temperature will transfer heat to the one at the lower temperature. There are three modes of the heat transfer. One is called the conduction. Conduction is the main mode of the heat transfer in the solids. So when you keep one end of a solid into contact of the system at higher temperature and the other end to the system at the lower temperature, there will be heat flow from higher temperature to lower temperature system, just like we are talking about here. So this system is at higher temperature, this system is at a lower temperature, and we took a uniform rod which is connecting both the systems. So this rod, initially what will happen, this rod will take heat and its temperature will increase. The temperature of this rod, each element will increase its temperature. This element will increase its temperature maximum, then this will increase its temperature less than the temperature of the element on the left. So if you divide this rod in small elements, you say, sir, dx length element we are taking. I'll say the temperature of this element will be T1, almost less than, slightly less than T1, and temperature of this end will be less than T2. So heat is being transferred from here to here. The temperature of this will be slightly lower than T1, okay? Then only heat can transfer from here to here. The temperature of this cannot be greater than this because heat is coming from this side. The temperature of this is rising because heat is coming from this side. So it cannot supply more heat so that the temperature is greater than this element himself. This will not transfer that heat. The temperature of this can never be greater than this because this is transferring the heat. So it will maintain its temperature greater than the temperature of this element. Same is happening here. Same is happening here. Same is happening here. Same is happening here. So they will increase their temperature, but not more than the temperature of the element on the left side, because left side element is supplying the heat. The temperature of any element cannot be greater than the element of the left side. So there will be a temperature difference between all the elements when we are going from this side to that side, and that is called the temperature gradient. And due to this temperature gradient, there is a continuous flow of the energy. So when this we are talking about this element is at higher temperature than this one, it will supply energy to this. But the same is happening on the left side element. This is supplying to this. This is supplying to this. And again, the other one is supplying to other one. So there is a continuous flow of the heat from this system to that system. And I have talked about the temperature gradient. This is the temperature gradient. When there is a lagged system, you are not allowing the energy to escape from here. That system is called the lagged system. Temperature gradient will be uniform, and the temperature gradient will be equal to T1 minus higher temperature minus the lower temperature divided by length of the rod. This is the temperature gradient. But for the unlagged system, we cannot write this expression. Unlagged system, there is a temperature gradient will be variable because we are allowing heat to escape from here. This is the graph for the unlagged system. So lagged system, unlagged system, they both are clear to you. This graph is important. Remember this. If they ask a question on the unlagged system, 95-96% student will not be able to answer the question of this. So you must be clear about the difference between lagged and unlagged system. Okay, lagged and unlagged system, you must understand the difference between both. Now let us talk about the heat current. So as I told you, like this, these are the two systems and we are connecting them with a rod, conducting rod. So heat is flowing from this side to this side, and this is called the steady state. So when a steady state is achieved, this is called the steady state. So heat current is the rate of flow of thermal energy from the system at higher temperature to one at lower temperature. So rate of flow of thermal energy from the system at higher temperature to one at lower temperature is called the heat current. It is represented by H, or sometimes we write dq divided by dt. So this is the rate. Heat energy being transferred per second. Heat energy being transferred per second is the heat current. So the energy which is being transferred per second is the heat current. Heat current is clear to you. Now we are going to talk about the steady state. Okay, this term is very important. Steady state and unsteady state are very, very important. See, there is a flow of energy, this continuously. This energy is being transferred to here. If the energy entering at this cross section, the rate at which energy is entering at this cross section is reaching, or then is equal to the rate at which energy is leaving at this section, then this rod is said to be in a steady state. This way you will not understand. There is a very beautiful example to make you understand this concept. See, let's take an example of a country, an hypothetical situation. So we are talking about a hypothetical situation. We are not relating with any country, okay? But you will be answering that. So in a country, there is a hypothetical country, there is a prime minister who is the topmost power in that country, topmost person in that country, most powerful person in that country, or who control all the money. There are state chief, then there are district collector, then there are blocks, then there is panchayat or village, and there is a common man. So who has all the power and all the money? The prime minister of the country. So he is the hottest person. Who has the least money or least power? common man, the cold person. So this kind of, if we talk in terms of the money, they have highest, they have minimum. Okay, so there is a difference. We can clearly see that there is a difference in the power or money. So let's say PM decide to send money to the common man, and this system is newly formed. Like before this government, there was some other government, and there is this this new government is formed in that system. So they all the chief of all the district, state, blocks, panchayat, they all are common men. They are newly elected people. So they are also poor. This person is poor, this person is poor, this person is poor, this person is poor, and this is the first day in their office. And this new government is formed, and this government, the Prime Minister decide, let's send some money to the common man. Let's distribute some money to the common man. Because they have money, they don't have. They are sending money to the common man. Okay. So they sent 100 rupees. So what will this person do? Will he transfer all the money to the person next to him? No. He'll keep 10 rupees and 90 rupees will be transferred. He'll keep 10 rupees, or maybe he will always keep money less than this person. Otherwise, this person will say, okay, you are going ahead me. You cannot keep money more than me, okay? You have to stay low. So he will hold 8 rupees. Now the 82 rupees are being transferred to the block. He'll keep 7 rupees. And the block, from there, the money goes to the Pradhan, Gram Pradhan, and there are 75 rupees. He kept 5 rupees, and the money reached to the common man is 70 rupees. This is just an example, okay? 70 rupees. So money started from here does not reach here. So this system is the unsteady state. This system is in unsteady state. And this process continue happening, like 100 rupees are released down every day, and they take their share, and 70 rupees are reaching to the common man. One day they will realize we have enough black money and we cannot anymore store money. Otherwise there will be a raid of ED. So what they will do is, now when Prime Minister releases the 100 rupees, they will directdirectly transfer that 100 rupees to the district. This person will say, no, I cannot anymore take this money out of it. So 100 rupees are being transferred. So same is with this person. When this person has collected enough money that if he continue collecting the money, then he will come into the he might fall into the trouble now. So he'll send the 100 rupees to this person, 100 rupees to this person, and this 100 rupees are reaching to the common man. So this state is called the steady state. Earlier it was unsteady state, now it has become steady state. So when 100 rupees going to this man, going to this, from here to here, from here to here, from here to here, so this is called the steady state. Now the rate of flow of money throughout is uniform. It is not changing. And such situation is called the steady state. Earlier it was unsteady state, now it has become this rod. Okay, you are dividing this rod into small length elements. Clear? This rod is divided into small length elements. So when heat is being transferred to this element, first it will increase its temperature. So to increase its temperature, it will hold some energy, and rest of the energy it will transfer to the other. Its temperature will slightly increase, but it has transferred energy to other. That will also increase. Some energy it will hold, and rest energy it will pass. So when energy entering dq by dt in, just the rate at which energy is coming in, is not equal to dq by dt out, then this is called the unsteady state. What is happening here? These elements are holding the energy and increasing their temperature. Once this process is done, the temperature has already increased, like the temperature of this has risen to this point, temperature of this, and there is a temperature gradient is there. Now the temperature of every element has already increased. Its temperature increased by this, by this, by this, by this, by this, by this amount, by this amount. Now they are not holding any more energy. So at any element, the dq by dt, which is dq by dt in, if becomes dq by dt out, if this becomes dq by dt out, then this is called the steady state. So when for any element dq by dt in becomes dq by dt out for any element of dx length, for any element of dx length, then this state is called the steady state. Then this state is called the steady state. Steady state is clear to you? Now there will be uniform heat flow. Whatever heat is entering at here will be leaving at here. So let's say 100 joule per second energy is entering from this end, 100 joule will be received by this system per second. Clear? Clear, 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 clear. A clear? One minute, no? Okay, so this is called the steady state heat current, and this example is clear. PM to common man, the money, how does money reaches? See, I told you about this batch, and this batch is the one of the best batch, because in this batch the top educators of the Unacademy are teaching for NEET 2024. This is a crash course, and the important thing about this batch is the price has changed. Now the price is not 7,999. If you use this referral code or the link given in the chat box, the price is, the new price is 5,499. And day before, or yesterday or day before that, it was 4,999, approximately equal to 5,000. Now 500 rupees has increased, and this is a limited period offer. So NEET End Game started today, which is the ultimate crash course for NEET 2024. Students preparing for NEET 2024 must join this batch. I am also teaching in this batch. These all faculties are teaching in this batch, and I hope you all are familiar with all the faculties. And the link of this batch is given in the description. Click on that link, go through the batch structure, and if you like it, if you want to enroll it, then join this batch at this limited period offer of 5,499 rupees. Don't forget to apply this Kailash 10 referral code. This is my referral code. With this referral code, the price will automatically reduce to 5,499 rupees or something like that. Na? So many of you have already enrolled for this batch. Today was the first class of this batch. I taught the rectilinear motion. We revised the rectilinear motion in a great detail. So if you are interested in this batch, then this is the best time, or today is the best time. Otherwise the price might hike anytime. Like last time also on 27th of December, I said the same thing. Okay, price might increase anytime, and on the 28th it was 7,999 rupees. and many students enrolled on 27th, and they got the like approximately they have to pay the 5,000 rupees. Again, there is this opportunity, 4599 rupees is the price, and this is for a limited period. Go and enroll for this batch. Politician and company, what do we know? No, let's not talk about the politicians of our country. We were talking about a hypothetical country. That was a hypothetical country, and I told you that in beginning of that example. Okay, we are talking about a hypothetical, and I clearly wrote that on the top of the page. Do check this course once. This course is like it is mentioned here, ultimate crash course. So if you are interested to be taught by this team, the link in the chat box will take you there, and just enroll for this batch. Okay. Now we are going to talk about the what is the, so we have talked about the temperature gradient, we have talked about the steady state, we have talked about the heat current. Now what is that rate of flow of the heat? If we connect a rod of length L, cross section of the rod, cross section area of rod is A. So cross section area means this area. Suppose this is a cylindrical rod, so the front part, the circular part area is A, which is shown here. The length of the rod is L. The temperature of the system is T1. The temperature of the other system is T2. In steady state, when steady state is achieved, steady state, what is the rate at which heat is flowing? So rate of heat flow, which is called the heat current as well. So when steady state is achieved, the rate at which heat is entering at this end will be equal to the rate at which heat is leaving this end. Okay. So heat current, which is H, or which is also equal to dq by dt. So this dq divided by dt will be directly proportional to area of this rod. So the more is the area of the cross section, more heat will pass through it. And this dq divided by dt is also directly proportional to temperature gradient. This dq divided by dt is also directly proportional to temperature gradient. So this dq divided by dt comes out to be minus ka Ka dt divided by dx, because temperature gradient is minus ka dt divided by dx. This K is called the thermal conductivity. K is called the thermal conductivity. K is called the thermal conductivity. This is the material property. Material property. This is the material property. So this heat current, which is H or dq divided by dt, in a steady state becomes K into A T1 minus T2 divided by L. This is the heat current. So heat current H is equal to T1 minus T2 divided by L upon Ka. L upon Ka is the heat current. So heat current is equal to T1 minus T2 divided by L upon Ka. We can relate this heat current with the electric current. So if there is a resistance and V1 and V2 are the potential across the ends of the resistance, then current will flow from the higher potential end to the lower potential end, and this current is given by V1 minus V2 divided by R. Similarly, this heat current is given by T1 minus T2 divided by RTH. This RTH, which is equal to L upon Ka, is called the thermal resistance. Thermal resistance. So this is called the thermal resistance. So rate of heat flow in the steady state is given by this formula. H is equal to T1 minus T2 divided by RTH. Always remember, this formula is valid for uniform rod. Uniform rod. Cross section should be uniform. Thermal conductivity should be uniform. Material should not change. Cross section area should not change. Then heat current can be written by this formula. The rate at which heat is flowing from the body at the higher temperature to one at the lower temperature is given by this formula. T1 minus T2 divided by RTH is the rate of heat flow in the steady state. Clear? A clear? There are the, I never go through a list like this, like few thermal conductivity values are given, but I have seen questions in JEE Main and NEET which are some like this kind of data or information based questions also they ask. That's why I added this table into this class. So you have to just keep the values of the thermal conductivity into the mind for few metals. Like aluminium, the thermal conductivity is 2 to 6 watt per meter per Kelvin. Okay, well, how does the unit of thermal conductivity we get? So dQ divided by dt, the unit of this is watt. Rate of heat flow is there, na? So this dQ divided by dt is equal to Ka T1 minus T2 divided by L. So unit of this is meter square. Unit of this is meter. Unit of this is Kelvin. So unit of Kelvin, unit of K is comes out to be 1 meter will cancel out. This is watt per meter per Kelvin. The unit of K will be or thermal conductivity will be this, thermal conductivity. Or unit of thermal conductivity can be joule per second meter Kelvin or calorie per second meter Kelvin. Okay, these are the unit of the thermal conductivity. So remember these values, at least have an idea about them. Aluminium at least remember 2 to 6, almost 225. Copper you have to remember that is close to 400. Close to 400. Sometimes they don't give the value of K. Iron that is close to 70. And lead which is 34. Nickel 88. Zinc, titanium 21. Okay, so few values you have to remember: aluminium, copper, iron, lead, nickel and titanium. These values keep in mind before going to exam. They might ask, mostly copper value is not given. Like copper, the most of the question are related to copper, and the value of copper is not, the thermal conductivity value for copper is not given. Then take the value of K approximately equal to 400. Okay. Okay, got it? So thermal conductivity is clear to you. So whenever we are talking about heat flow, rate of heat flow. So rate of heat flow, rate of heat flow. So there is a system at T1 temperature. There is a rod connecting that system with the one at T2 temperature. The rod length is L. Cross section area is A. Thermal conductivity is K. Then dQ by dt, you write T1 minus T2 divided by thermal resistance. And this thermal resistance comes out to be L upon Ka. Clear? Thermal resistance. So more is the thermal resistance, less will be the heat flow. Less will be the heat flow for the same temperature difference. So heat flow depends on few parameters. One is the temperature difference. More is the temperature difference, more will be the heat flow. Thermal resistance. Thermal resistance is equal to L upon K. The length of the rod should be small for more heat flow. Thermal conductivity should be high. Cross section area should be high. So out of these all options, copper is the best option which has highest thermal conductivity, and mostly copper is used for the conduction type of processes. Okay. So let's have a look on what we have covered till now. We started the topic heat energy, we defined, we talked about the calorie, what is the 1 calorie heat. Then we talked about the conduction mode of the heat transfer, first mode of the heat transfer, which is the conduction. I hope conduction is clear to everyone, and simple information type question can be asked on the conduction. Where do you see the conduction? Like some process they might ask, you must be able to relate. There is no net mass movement, molecules transfer energy during the collision. So related to this also question can be framed. Temperature gradient. So when two systems are connected by the rod, there will be temperature drop when we move from the system at higher temperature to the one at the lower temperature. Lagged rod, temperature gradient will be constant, and that will be equal to higher temperature minus lower temperature divided by length of the rod. Unlagged rod, temperature gradient will be like this. Unlagged rod allow the heat escape from this part. Lagged rod only heat entering here, leaving here. There is no heat flow at this part. At this side there is no heat flow. Heat current is the rate of the flow of the thermal energy from the system at the higher temperature to one at the lower temperature. Steady state is the state when temperature stop changing for any element of the rod. This hypothetical situation was there. Then ultimate batch was there. Rate of heat flow, which is the heat current. So heat current is directly proportional to the area of the rod. It is directly proportional to the temperature gradient. So heat current comes out to be minus ka K dt by dx. In a steady state, this dt by dx for the lagged rod becomes T1 minus T2 divided by L. So we put minus ka dt by dt equal to T1 minus T2 divided by L. So heat current we got like when we take them below the L, like, so we get T1 minus T2 divided by L upon K, and heat current comes out to be T1 minus T2 divided by RTH. So RTH is the thermal resistance. Just like the electric resistance, there is a potential difference V1, V2 across the resistance. Current is V1 minus V2 divided by R. So here temperature difference is T1, T2 across the rod. Then heat current can be written like T1 minus T2 divided by thermal resistance. So thermal resistance is equal to L upon Ka. This is the quick recap of the content we have covered till now, and this is all about the thermal conductivity of the metals. So there is a question number 1. 4 rods with different radii R and length L are used to connect two reservoirs of the heat at different temperatures. Which one will conduct most heat? Which one will conduct most heat? So heat conduction will be maximum for which case? Okay. So there are two reservoirs. Let's say this is the first one and this is the second one. We are connecting both with the rod. So let's say this is at T1 and this is at T2. Length L, radius is given as R, so area becomes pi R square. Okay, so rate of heat flow, which is heat current, is equal to T1 minus T2 divided by L upon Ka. So for this to be maximum, L should be minimum and A should be maximum, and K also should be maximum. So A maximum means R should be maximum. So which R is maximum? There R is 1, 1, 2 and 2. So out of these two can be the possible option. L should be minimum. L is 1 by 2, 2 and 1 by 2. Which value of L is minimum? 1 by 2. So 1 by 2 is here, 1 by 2 is here. But R is maximum is here. So fourth option will be the correct option. R maximum, L minimum is in the fourth option. The fourth option will be the correct option. So we have to just compare for the heat current to be maximum, the thermal resistance should be minimum, and thermal resistance is equal to L upon Ka. So L upon K should be minimum, L should be minimum, area should be maximum, means R should be maximum. This was the question number 1. There is question number 2. A rod of 1 meter length and area of cross section 1 centimeter square is connected across two heat reservoir at temperature 100 degrees Celsius and 0 degrees Celsius as shown. So temperature at this end is 100 degrees Celsius and the temperature at this end is 0 degrees Celsius. This rod of length 1 meter, this is 1 meter length rod with area of cross section A is equal to 10 raised to the power minus 4 meter square. The heat flow per second through the rod in the steady state. The thermal conductivity of the rod is given as 0.09 kilocalorie per meter per second per degree Celsius. So heat current we have to find in this case. What will be the heat current in this case? A option. What will be the heat current in this case? Please don't forget to like the session if you already like it. Like the session, share among your friends, subscribe this YouTube channel. So the heat flow per second through the rod in the steady state will be, the heat flow is given by H is equal to T1 minus T2 divided by L upon Ka. So Ka we can take up to 0.09 kilocalorie. Keep that in mind. Into area. Area is 10 raised to the power minus 4. Temperature difference is 100 divided by length is 1 meter. So we get 9 into 10 raised to the power minus 4 kilocalorie per second. A option is the correct option. Is this clear to everyone? So question number 1 is clear to everyone. So 9 into 10 raised to the power minus 4 kilocalorie will be the correct answer of this question. This was the question of the conduction. So conduction we have studied. Conduction part is done, like rate of heat flow. This kind of questions can be asked on this part. Now we move if there are two rods connected in series like this. So there is a rod. This rod is rod 1. So rod 1 and this is rod 2 and they are connected in series with each other. The temperature of this reservoir is T1 and of this reservoir is T2. What is the rate of heat flow? What is the rate of heat flow from this system to that system? And what is the temperature of this junction? So heat enter at this end and passes through this in a steady state and the same heat is reaching there. So what we do is we simply say consider them like two resistors. Mark resistor R1, R2, here T1, T2. The temperature of junction will be T, heat current is H, So we can write H is equal to T1 minus T divided by R, and that is equal to T minus T2 divided by R. This is R1, this is R2. From here we can find temperature T, which will be equal to T1 R2 plus का T2 R1 divided by R1 plus का R2. So just find thermal resistance and you will get the temperature of the junction. Heat current can also be written like T1 minus T2 divided by total resistance will be equal to R1 plus R2. So total resistance is equal to R1 plus R2, just like current electricity series combination of the resistors. Then current electricity series combination of the resistors, we directly add both the resistors and we find the equivalent of the resistance. So equivalent will be equivalent resistance of series combination of two rods RTH equivalent RTH1 RTH2. So this will be the equivalent thermal resistance of both the rod, combination of this rod. So when two rods are connected in series like this, the equivalent thermal resistance is equal to this resistance plus this resistance. So net heat current will be equal to T1 minus T2 divided by equivalent resistance, which is R1 plus R2, which is R1 plus R2. Okay. So equivalent thermal conductivity, sometimes question on equivalent thermal conductivity are asked. So what is equivalent thermal conductivity? There are two rods which are connected in series, and they both are connected across T1 and T2. So what we want to do is we want to replace this combination, with a rod of single material and similar dimension. So what is the meaning of the equivalent? We have to we want to replace this combination with a single rod which is made of a single material, and the dimensions would be same, like this length is L1, like this length is L1, this length is L2. So what we have to do is we have to take a single rod. The total length of that single rod should be equal to L1 plus L2. The total length of that single rod should be equal to L1 plus L2. Area of this rod is A. Area of this rod is A. The area of this rod should also be equal to A. But it should be made of single material. What should be the thermal conductivity of that single material, which gives us same rate of heat flow which is given by this material. So there is a heat flow, let's call it H is the rate of heat flow. The same heat current is flowing in this rod. The same current is flowing in this rod. Then this equivalent of this combination is this rod. So simply we write R1 plus R2 is equal to R. Okay, R equivalent. R1 is L1 upon K1A. R2 is L2 upon K2A. R equivalent is L1 plus L2 divided by K equivalent into A. So K equivalent comes out to be L1 plus L2 divided by L1 upon K1, L2 upon K2. So K equivalent will be equal to L1 plus L2 K1 into K2 divided by L1 K2 L2 K1. This will be the equivalent thermal conductivity of this combination. Equivalent thermal conductivity of this combination will be this. So when two rods are connected in series, so in JE as well, like in NEET, so obviously they can ask this question. They are asking in JE main this kind of questions. So you must be prepared for this kind of question of K equivalent. You want to replace these two rods with a single rod, and what should be the equivalent thermal conductivity of that rod? That is given by this formula. So you have to keep the same dimension. Dimension should be same. Like total length of this combination should be equal to total length of that rod. Area. When you connect two rods in series, their area are same. The area should be same for this rod as well. Then you get the just resistance of that combination should be equal to resistance of this single rod, and you get the thermal conductivity. There is a question. A wall has two layers, A and B, each made of a different material. Both the layers have the same thickness. The thermal conductivity of the material of A is twice that of B. Under thermal equilibrium, the temperature difference across the walls is 36 degrees Celsius. The temperature difference across the layer A is under the thermal equilibrium, the temperature difference across the wall is 36 degrees Celsius. So let me make you diagram of this. So both layers have the same thickness. These are two layers, okay? Let's say the thickness of this is D and this is also D. Here the temperature difference, if the temperature on this side is 0 degrees Celsius, then temperature on this side is 36 degrees Celsius. This is A and this is B. The temperature difference across the wall is 36, then the temperature difference across this layer. So the temperature at this junction will be T. Temperature at this junction is T, so they are asking 36 minus ka T. What is the value of 36 minus T? The temperature difference across the layer A. Thermal conductivity of A is twice that of the, so this is 2K, and the thermal conductivity of B is K. So what will be the value of the temperature? So they are asking temperature difference, not temperature. Can you solve this question? Anyone? How do we solve this kind of question? So heat will be flowing like this. So they both, the same heat is passing through them. That's why this and this are called in series. So we make two resistances here. We say the temperature of this is 36 degrees Celsius, 0 degrees Celsius. We want to know the temperature of this point. The resistance, this resistance will be equal to L upon 2Ka. L की जगह D use करेंगे, ठीक है? R2 is equal to D upon Ka. Okay. So let's say this resistance is equal to R, and this will become 2R. So here is the situation like this. 36 degrees Celsius. The resistance is R. Temperature T, the resistance is 2R. 0 degrees Celsius. H, heat current is flowing through it. So H will be 36 minus ka T divided by R. That is also equal to T minus 0 divided by 2R. R gets cancelled out. 3T is equal to 72. So T will be equal to 24 degrees Celsius. T will be equal to 24 degree Celsius. So T is 24 degrees Celsius. So what is the temperature difference? So delta T 1 जो होगा 36 minus 24, 12 degree Celsius. So temperature difference is 12 degree Celsius. This will be the answer. Sometimes we might commit a mistake here and can answer fourth option. So 12 degrees Celsius will be the answer of this question. So a wall has two layers A and B, each made of the different material. Both layers have the same thickness. The thermal conductivity of the material of A is twice that of the B. The under thermal equilibrium, the temperature difference across the wall is 36 degrees Celsius. The temperature difference across the layer A is clear. Delta T will be 12. Okay, delta T will be 12. This was the question number 3. What if the rods are connected in parallel? Sometimes rods are connected in parallel. There is this system and there is this other system. Rods are connected like this. So there will be heat current H1 and there will be heat current H2. So net heat current, the rate, net flow of heat or we say rate is equal to H1 plus H2. This will be the net flow of the heat. Okay, net flow of the heat will be H1 plus H2. H1 is given by T1 minus T2 divided by R1. H2 is given by T1 minus T2 divided by R2. The equivalent thermal resistance will be given by 1 upon R1 plus 1 upon R2, because net heat rate flow will be equal to T1 minus T2 divided by R1, T1 minus T2 divided by R2, and this is equal to T1 minus T2 1 upon R1 plus ka 1 upon R2. So we can write it like T1 minus T2 divided by R equivalent. So R equivalent will be equal to, just like parallel combination of the resistances, there will be parallel combination of the two rods will be treated like the same way. Parallel combination of two rods will be treated like the same way. So when we say what will be the equivalent thermal conductivity, so we want to replace these two rods with a single rod. We want to replace these two rods with a single rod. Area of this rod is A1 and that of this rod is A2. So the area of this should be equal to A1 plus ka A2. Both rods are of same length. So this is also of same length, but this is made of single material. So equivalent thermal conductivity, you will find questions only like based on these formulas only. Whatever concept I am teaching, you solve any module of any institute, you will find the questions related to these terms only. So equivalent thermal conductivity. Equivalent thermal conductivity. So 1 upon R1 plus 1 upon R2 is equal to 1 upon R equivalent. So L K1 upon A1 K1 upon L, A2 K2 upon L, A1 plus A2 K equivalent upon L. So K equivalent comes out to be A1 K1, A2 K2 divided by A1 plus ka A2. This is the equivalent thermal conductivity in case of two rods connected in parallel with each other. Okay. When rods are connected in parallel, the equivalent thermal conductivity will be given by this formula. So there is a question number 4. Two rods of same length and material transfer given amount of the heat in 12 seconds when they are joined end to end. When they are joined lengthwise, then they will transfer same amount of heat in same conditions. See, there will be a practice session as well on this, on these 3 topics. And practice session will be, tomorrow is Wednesday, Thursday. on this weekend. I'll share the link in the description. This weekend on Saturday there will be practice session on these two topics. Okay, 4 p.m. to 5 p.m. will be the time. Otherwise, without practice, you will not be able to complete these topics. So question number 4 is there. Two rods of same length and material transfers given amount of heat in 12 seconds when they are joined in end to end. When they are joined lengthwise, then they will transfer the same amount of heat in the same condition. So in the first case, they are joined in series combination. Okay, they are joined of length L, length L. So T1, T2. So the rate of heat flow will be T1 minus T2 divided by the resistance will be 2R. When they are connected lengthwise between the same system, T2, T1. Now the heat current of both, the equivalent resistance will be equal to R by 2. So heat current will be equal to T1 minus T2 divided by R by 2. This times 2 times heat current in series. So heat current in parallel will be 2 times heat current in the series. So in this case, not 2 times, 4 times. There is T1 minus T2 divided by 2R. So if you want here 2R, then you will have to multiply and divide with 2. So it will become 4, 4 goes up. So 4 times heat current of the in the series will be the heat current in the parallel. So when you connect two rods in series and you connect them in parallel, identical rod, in parallel there will be 4 times heat current. So rate of heat flow will become 4 times in case of two identical rods, and this concept you have to remember. So when you connect two rods in the series and the same two identical rods in parallel there will be heat flow 4 times. So same amount of heat you want to flow, then the time taken will be 1/4. So initially it was taking 12 seconds, then in this case it will take only 3 seconds. The same amount of heat can be flown in the 3 seconds because now rate is 4 times. Okay, this is a very standard question. No, not two rods, same length and same material given some amount of this when they are joined end to end. When they are joined end to end, that means series combination. When they are joined lengthwise, when you connect them lengthwise, then this amount, the heat flow will be 4 times, and time taken will be 1/4. Okay. See, the resistance of this combination, series combination, is 2R. So heat current in series combination will be T1 minus T2 divided by 2R. The resistance in parallel combination is R by 2. So heat current in parallel combination will be T1 minus T2 divided by R by 2. R by 2 we can write like this. If we multiply here with 2 and multiply here with 2, then this term becomes heat current in the series combination. So heat current in the parallel will be equal to 4 times heat current in the series combination. The heat current in the parallel will be equal to 4 times heat current in the series combination. So series combination is transferring some amount of heat in 12 seconds. Now you are transferring the same amount of heat at a 4 times rate. It will take less time now. So in 3 seconds you will be able to transfer the same amount of heat that is being transferred in the 12 seconds. Now is this clear to everyone? Okay. Heat flow through a spherical shell. You don't have to remember the derivation of this. Okay. You don't have to remember, just remember the formula which I am going to tell you. Derivation is the resistance of this. We consider a small shell and we write the resistance of that. That comes out to be dr divided by K into 4 pi r square. We add all the resistance and the thermal resistance of this shell comes out to be 1 upon 4 pi K. 1 upon A minus का 1 upon B. So B minus का A divided by AB. This is the resistance of the shell. So this is a hollow shell. Hollow shell of inner radius A and outer radius B. So there is, let's say this is at the higher temperature, the heat will be flowing like this. Heat will be flowing like this to the temperature surrounding, like this. Heat will be flowing like this. So resistance, thermal resistance of this will be equal to B minus A divided by 4 pi K A into B. So this will be the thermal resistance of this shell. So heat current H is given by T1 minus ka T2 divided by thermal resistance, which is B minus ka A 4 pi K A into B. Remember only these two formulas, not more than that is required. Okay. So remember the formula of the thermal resistance and the rate at which heat is flowing from inside to outside of this shell is given by that formula. Okay. So heat flow through the spherical shell is equal to T1 minus T2 4 pi K AB divided by B minus ka A. Now we are moving to the second mode of heat transfer. That is only theory part we have to cover. That is called the convection. So convection you all have seen in this. In convection, see, in conduction there was no net mass movement involved while heat was being transferred. But in convection, heat transfer takes place along the mass movement. Mass is taking heat from one place to another place. So convection is the transfer of heat flow from one place to another place due to the movement of the fluid. Fluid can be air as well. Air or fluid, liquid. Through them you are transferring the heat. The liquid or the gas is taking heat along with them, and this kind of heat transfer is called the convection. There are two types of the convection. Two types of convection are there. You have to remember these. Natural convection, which occur naturally. Natural convection, like fluid motion caused by the buoyancy force. So hot air, hot air is lighter than the density of the hot air is less as compared to cold air. So hot air will lift up due to the buoyancy and cold air will come down, and there is a movement of the hot air in upward direction, and that is due to the buoyancy or the difference in the density. That kind of convection is called the natural convection. There is a forced convection. Fluid is forced to flow over the surface by external means like fan. Using fan you can cold the few things. You can try to cool a thing, like when you are drinking the tea, by blowing air you are trying to cool it, and that is also convection, and that is called the forced convection. And if you leave the hot cup of tea to cool it down naturally, then that will be considered as the natural convection. When you start blowing the air, it will become forced convection. Example of the convection are boiling water. When you are boiling the water, just before evaporating, there is a movement in the water. And the water at bottom is having higher temperature and low density. It will come upward, and the cold water will go downward. There is a movement of water when you are boiling it. Hot cup of tea, you have seen the smoke coming out of the, we don't call it a smoke actually in case of tea, we call it something else. Air cooled engines. You have seen the engine of the bike. There are fin on the engine, like there is a extended part of the metal which help in cooling the engine through convection. So more area is exposed to the air cooled engines. Sea and land breezes and chimney and ventilation in the rooms, they all work on the principle of the convection. So heat convection is the second mode of heat transfer, but the numerical part of convection is not in our syllabus. The numerical questions are not generally asked on this. Only information based question they might ask. So convection, all these things you have to keep in mind. There is a net mass movement while heat transfer is taking place. Okay. Now let us talk about the one more very important topic of heat transfer, and that is the radiation. Radiation and conduction are both have equal weightage. Like either one question can be asked from radiation or from conduction. They both are equally important, and their weightage is equal, their length is also equal. Every body above temperature 0 Kelvin radiate electromagnetic radiations of several wavelengths to the surrounding. Anybody, even my body, at temperature 0 Kelvin, at temperature above 0 Kelvin, will radiate energy. The energy is being radiated by any body which has temperature greater than 0 Kelvin. 0 Kelvin minus 273 degrees Celsius. Obviously, the human body will also be radiating energy because that also has temperature greater than 0 Kelvin. These polychromatic radiations are called the thermal radiation, and the radiation being emitted by the body is the thermal radiation. The power radiated depends on few things. The amount of radiation will depend on few things, and one of them is temperature, body temperature. So if a body has higher temperature, it will radiate more energy. Nature of the surface. So there are two, basically we categorize bodies in two categories, black body and normal body. So black body radiation will be different for the same conditions of the as of the normal body. Normal body will be radiating different amount of the energy. So it will depend on the nature and area of the emitting surface. More is the area of the emitting surface, more will be the radiation emitted by the body. So radiation, any body which has temperature greater than 0 Kelvin will be radiating energy, and these radiation which are electromagnetic radiations are called the thermal radiation, and the power radiated depends on few parameters: temperature, nature of the area, and the total nature of the surface and the total area of the surface. There is a one body which is called the black body. Okay, black body. So when a body is kept, suppose this is a body, okay, this body is kept in the room or somewhere, it is emitting energy. Every body which has temperature greater than 0 Kelvin is radiating energy. We are not interested in that energy. There will be other bodies as well in its surrounding. They also will be radiating energy, and their energy will be incident on it. This energy is called the Q incident. Dot, because we are talking about the rate per second, the energy incident to this body is the Q dot in. Some part of this energy is reflected, Q dot R. Some part of this energy is absorbed, Q dot A. And some part of this energy is transmitted, which is Q dot T. So any body receiving energy from its surrounding, it will reflect some energy will be transmitted through it, some energy will be absorbed by this body. The some part of the incident energy will be absorbed by this body, reflected by this body, and transmitted by this body. Got it? These are the energy. All the energies are due to the surrounding bodies. So surrounding is providing energy to this body, and fraction of that is being absorbed, fraction of that is being reflected, fraction of that is being transmitted. And apart from these energies, it is already radiating energy, which is E emitted. It is also emitting energy due to its temperature greater than 0 Kelvin. So these all energies are involved here. So there are some coefficient, absorption coefficient, which is Q dot A divided by Q dot N. So fraction of the energy which is absorbed is absorption coefficient. The reflection coefficient is Q dot R divided by Q dot N. And transmittance, we call transmittance T equal to Q dot T divided by Q dot incident. So fraction of the incident energy which is transmitted is called the transmittance, absorptance, reflectance and transmittance. These are three very important terms. If you add all these three, A plus R plus T, they are equal to 1. They are equal to 1. If you add all these three, they are equal to 1. Got it? Okay. Now, black body. So black body has a special characteristic. A body which absorb, a body which absorb all the radiations incident on it is called black body. A body which absorb all the radiation incident on it is called the black body. So for the black body, Q dot absorbed is equal to Q dot incident. This is the special characteristic of the black body. The rest of the bodies will definitely reflect some part of the energy. They will not completely absorb it, incident energy. So absorbed energy is equal to incident energy, and that is the characteristic of the black body. So black body absorb all the energy incident on it. Here A will be equal to 1. A will be equal to 1. For the black body, A will be equal to 1. Black body is a good emitter as well. Good emitter as well. So which absorb most of the energy will emit, will be a good emitter as well. Means it will also be emitting the energy. So what is happening here? This is the body. Some energy is incident on it. Some part of that energy is reflected. So this energy is of no use to us. Some part of this incident energy is absorbed by this body. This body absorbs some energy. Okay? Some energy is absorbed by this body. So this absorbed energy will increase its temperature. This absorbed energy will increase the temperature of the body. But what is happening here? This body is also emitting energy because of its temperature is greater than 0 Kelvin. This is emitting energy. So if this emitted energy is greater than absorbed energy, the body will net lose heat. If emitted energy is less than absorbed energy, the body will net gain the heat and its temperature will increase. So we have to compare these two energy, absorbed energy and emitted energy. So we have formula for the emitted energy. We will relate and find the emitted absorbed energy, and then we will see if the body is net losing heat or gaining heat. So how many energies are involved there? Incident energy, part of that gets reflected, that is of no use. Some part of the energy is absorbed. That absorbed part will increase That absorbed part is actually the energy which is taken by the body, but body is also losing energy because of radiation. So if taken part of the energy, the incident energy which is absorbed is equal to emitted energy, the temperature of the body remain constant, because neither it is losing nor it is gaining energy. But if it is losing at a higher rate and absorbing at a low rate, then net temperature of the body will fall. If it is losing at the low rate but absorbing at the high rate, the temperature of the body will rise. And these all the phenomena we are going to talk about. What is the incident energy, on what factors this incident energy depends, what is the absorbed energy, reflected we are not very much interested, what is the emitted energy. So black body is a body which absorb all the energy. In case of black body, there is no this energy, not this energy. All the radiation falling on the black body is being absorbed. All the radiation falling on a black body is being absorbed. Clear to you? Okay. So there is a Stephen Boltzmann law which tells us what is the rate of radiation. So the thermal power radiated by a black body per unit area is directly proportional to the fourth power of its absolute temperature. So let's say there is a black body. This is the black body of A cross section A surface area. There is a body of black body of A surface area. So surface area of this body is A. The temperature of the body is T. So they are saying this body will be radiating energy. This is different from the incident energy. This body is losing heat, and this radiate and rate of energy radiated, E dot emitted, is directly proportional to temperature to the power 4. And this is per unit area. Per unit area. So power emitted will be equal to, if area is given, then power emitted by black body comes out to be sigma A T to the power 4. So this is the rate at which a black body is emitting energy. Sigma A T to the power 4. Sigma is called the Stephen's constant. And value of sigma is 5.67 into 10 to the power minus ka 8 watt per meter square Kelvin to the power 4. So this is the value of sigma. So any body which like temperature of that body is known to us, then we can find for black body of A surface area, temperature T, the energy radiated by it will be equal to sigma A T ki power 4. Sigma A T ki power 4 will be the energy radiated by the black body. There is a concept of emissivity. So let's say there is a body of, there is this body, okay, and I copy this. How to paste? Let me draw one more diagram. There are two bodies, okay. This one is black body. And this is identical normal body. Identical normal body. So they both are identical, okay. This is black body, this is normal body. The temperature of black body is T. The temperature of the normal body is also T. So power of black body is given by sigma A T to the power 4, radiation power. Then radiation power of the normal body is given by E sigma A T to the power 4, where E is less than or equal to 1. E is equal to 1 for black body. For black body. And this E is called the emissivity. E is called the emissivity. E is the emissivity. So by knowing the value of E, you can find the radiation power of any body. If you know the value of E and temperature of any body, surface area of that body, you can directly write at what rate that body is radiating energy. At what rate that body is being radiating energy. So black body will be radiating at the maximum rate. For the black body, value of E is 1. So if there are two bodies, one is normal body, one is the black body, and they have the same temperature, the black body will be radiating at the more rate than the normal body. So this is the rate of emission is maximum for black body of identical shape and temperature equal to other bodies. So if there is a black body and a normal body of identical shape and same temperature, black body will be radiating at the maximum rate. So there is a question. The energy emitted per second by a black body at 1227 degrees Celsius is E. If the temperature of the black body is increased to 2727 degrees Celsius, the energy emitted per second in terms of E will be. What will be the energy emitted in terms of E? Rate of energy emitted you have to find. Okay. So what is happening here is, always keep one thing in mind. You have to put the temperature in terms of in Kelvin only. So temperature, initially the temperature was 1227 plus 273, which comes out to be 1500 Kelvin. And the second time temperature becomes 2727 plus 273. And this is 3000 Kelvin. The temperature becomes 2 times. The rate of emission is directly proportional to temperature to the power 4. So the temperature becomes 2 times. And power of 2 to the power 4, this becomes 16 times. So 16E will be the answer of this question. So rate of emission will become 16 times. The energy emitted per second by a black body is this, then the temperature of the black body is increased to this, then the energy emitted per second in terms of E will be 16E. 16 times will be the energy emitted per second. There is a Kirchhoff's law of radiation. There is a Kirchhoff's law of radiation. What does this law say? So there is a black body in surrounding of T0 temperature, and there is a normal body, identical normal body in surrounding of T0 temperature. So this surrounding is at T0 temperature, this body has temperature T, surrounding temperature is T0, and these bodies are kept there for very long time. The temperature of this body will becomes T0 in thermal equilibrium, and they are kept for very long time. Temperature of body becomes temperature of the surrounding, and this is a black body. Okay, this is a very beautiful experiment. So there is a black body which is kept in a surrounding of temperature T naught. So the rate at which it is receiving energy and rate at which it is emitting energy are same. So E dot emitted, we know this formula, that is sigma A T naught ki power 4, because the body temperature is T naught. So this, at this rate it will be emitting energy. Energy absorbed, because this is a black body, so energy incident is equal to energy absorbed, and the temperature of this body is not changing. So this is equal to energy emitted. So this is the energy emitted and this is energy absorbed. This energy is absorbed, this energy is emitted, net energy remain constant. That means these both energies are same. So energy absorbed is equal to energy incident is equal to sigma A T naught ki the power 4. So with the help of this, we can find incident energy is equal to sigma A T naught ka power 4. So if you keep a body of A surface area in a surrounding of temperature T naught, the body will be receiving energy at a rate of sigma A T naught ki power 4. Now we are talking about a normal body. So there is a normal body, okay? So normal body is there. What is happening to this body? After some time it will also attain thermal equilibrium. The temperature of this body will become T naught, okay? What is the rate of energy incident on it? Sigma A T naught ki power 4. That will remain same. If you replace this black body with the normal body, are you changing the surrounding condition? No. So the incident energy does not depend on that body. It is a black body or normal body. The incident energy will be same. But absorbed energy depends on the body. Absorbed energy will be equal to A times sigma A T to the power 4. This is the absorption coefficient, okay? This body will be radiating energy, E dot radiated, that is equal to E sigma A T naught ki power 4. And because temperature is constant, T is constant, so these two energy must be same. When you equate both, you get A is equal to E. Wow, we got A is equal to E. So for any body, the incident energy will be equal to sigma A T naught ki power 4. But absorbed energy will be equal to E sigma A T naught ka power 4. So now you don't have to write A for the absorbed energy. You can directly write E sigma A T naught ka power 4 will be the absorbed energy if a body is kept in a surrounding of T naught temperature. So absorbed energy now we can calculate. Emitted energy depends on the temperature of the body. Absorbed energy depends on the temperature of the surrounding. So when we talk about, so Kirchhoff's law of radiation is over, okay? So when we talk about the rate of cooling or rate of heating, so rate of cooling and rate of heating, so there are two cases. Let's talk about rate of cooling first. Rate of cooling. So rate of cooling means rate at which temperature is changing, dT divided by dt. So there is a body which has temperature greater than surrounding. So surrounding temperature is T naught. Body temperature is T. This is absorbing some energy and radiating some energy. So if radiated energy is greater than absorbed energy, that means it is losing energy. So temperature will, rate of cooling is minus dT by dt because temperature is decreasing now. So its temperature will fall. Its temperature will fall. So rate of emitted, energy radiated is greater than absorbed energy, then there will be cooling. So what is the rate of radiation? So rate of radiation is E sigma A T to the power 4. The radiation depends on the temperature of the body. Absorbed energy we just derived. Q dot absorbed is equal to E sigma A T naught ka power 4. So absorbed energy depends on the surrounding temperature. Radiated energy depends on the body temperature. So rate of heat loss, the rate at which heat is being lost by the body is equal to this minus this. So E sigma A T to the power 4 minus the T naught ka power 4. So this is the rate of heat loss. Rate of heat loss we can write minus ms dt divided by dt. E sigma A T to the power 4 minus ka T naught ka power 4. So minus dt divided by dt, which is the rate at which temperature is falling. This is called the rate of cooling. Rate of cooling comes out to be E sigma A divided by m into s T to the power 4 minus ka T naught ka power 4. S is called the specific heat capacity. S is called the specific heat capacity. So rate of cooling is given by this formula, E sigma A divided by m into s T to the power 4 minus ka T naught ka power 4. The rate of heating is when body temperature is less than surrounding, then it is net taking the heat. So dt divided by dt is the rate of heating. You simply multiply with by minus E sigma A divided by m into s T naught ka power 4 minus ka T ka power 4 is the rate of heating. This is called the rate of heating. So rate of heating is this, E sigma A divided by ms T to the power 4 minus T naught ka power 4 minus ka T to the power 4. In this case, surrounding temperature will be more as compared to body temperature. So rate of cooling, rate of heating. There is a Newton's law of cooling. I think this is removed from your syllabus, but on the safe side we are going to cover this small topic. So we know rate of cooling is equal to E sigma A divided by m into s T to the power 4 minus ka T naught ka power 4. If temperature difference between surrounding and the body, surrounding and body is small, if temperature difference between the surrounding and the body is small, what is the temperature difference? T minus ka T naught, which is delta T, small as compared to T naught. So delta T is very, very small as compared to surrounding temperature. Then in place of T we can write delta T plus T naught. We put that there. So minus ka dt by dt, which is rate of cooling, becomes E sigma A divided by m into s T to the power 4, which is T naught plus delta T to the power 4 minus ka T naught ka power 4. So minus ka dt by dt becomes, you take T to the T naught common, E sigma A T naught to the power 4 divided by m into s, it becomes 1 plus delta T divided by T naught to the power 4 minus ka 1. Binomial expansion of this, minus ka dt divided by dt becomes E sigma A T naught ka power 4 divided by ms. Binomial expansion will be 1 plus 4 delta T divided by T naught minus 1 and minus dt divided by dt comes out to be E sigma A T naught ka power 3 divided by m into s into delta T. 4 will also be there. And delta T is temperature difference between the body and the surrounding. So rate of cooling becomes directly proportional to the temperature difference between the body and the surrounding. And this is called the Newton's law of cooling. So Newton's law of cooling says rate of cooling is directly proportional to temperature difference between the body and the surrounding is the rate of cooling. So rate of cooling is directly proportional to temperature difference between the body and the surrounding. There is a question based on that. When the temperature of the body is 80 degrees Celsius, its rate of cooling is 4 degrees Celsius per minute. And when the temperature becomes 50 degrees Celsius, the rate of cooling becomes this. Then the temperature of the surrounding is. Okay. So how do we solve this kind of question? So rate of cooling minus ka dt by dt, let's say equal to k times T minus T naught. It is directly proportional to temperature difference. So proportionality constant we are using k. They are saying it is cooling at a rate of 4 degrees Celsius per minute. And this is equal to k times 80 minus ka T naught. Okay. When the temperature of the body becomes 50, it is cooling at a 2 degrees Celsius per minute. So this is k times 50 minus ka T naught. We divide both. 100 minus ka 2 T naught is equal to 80 minus ka T naught. So T naught is equal to 20 degrees Celsius, and this will be your answer. If you understand this concept of rate of cooling, Newton's law of cooling, then you have to remember this formula only. The rate of cooling is directly proportional to temperature difference between the body and the surrounding. There is an average form of Newton's law of cooling. This is also a very important form. So let's say a body has temperature T1 and in delta T time, the temperature falls to temperature T2. So average rate of cooling is equal to k times average temperature minus ka surrounding temperature. So what is the formula? T1 minus ka T2 divided by delta T is equal to k times average temperature will be T1 plus T2 divided by 2 minus ka T naught. So this is the formula of average form of the Newton's law of cooling. Average form of Newton's law of cooling is T1 minus T2 divided by delta T equal to k times T1 plus T2 divided by 2 minus ka T naught. We will have a break very soon. So we are just about to complete this topic, this part of the heat transfer. After heat transfer, we will have a 15-minute break, and then we will start the thermal expansion and the calorimetry part. Okay. So there is a question. A body takes 4 minutes to cool from 100 degrees Celsius to 70 degrees Celsius. If the room temperature is 15 degrees Celsius, then how many minutes will it need to cool from 70 degrees Celsius to 40 degrees Celsius? So 70 to 40, what will be the time taken by this body? This body takes 4 minutes to cool from 100 to 70. So we apply this formula 2 times here. So this behave like T1 and this behave like T2. So T1 minus ka T2 divided by delta T is equal to k times T1 plus ka T2 divided by 2 minus ka T naught. This is the formula. So you put 100 minus ka 70, this becomes 30, divided by time is 4 minutes, is equal to k times 100 plus ka 70 divided by 2. So 170 divided by 2 becomes 85. Minus ka surrounding temperature is 15 degrees Celsius. Okay. They are saying how long it will take from 70 to 40. So 70 minus ka 40, which will be 30 divided by t. And the average of this 70 plus 40 divided by 2, this will be 55 minus ka 15. We divide both. 30 gets cancelled out. T divided by 4 is equal to, this is 70 divided by 40. So T is equal to 7 minutes. It will say take 7 minutes to cool from 70 degrees Celsius to 40 degrees Celsius. The same temperature drop will take twice the, like 7 minutes when temperature has already fallen from to 70 to 40, yeah, falling from 70 to 40 degrees Celsius. Okay, let's take a small break and then we start the Wien's displacement and the thermal expansion part and the calorimetry part of the physics. There are only 20 slides remaining. After 20 or 25 slides are remaining, and then this class will be over. So there is a small break. I have to add some slides as well. So class resume at it's 7:22 na. At 7:40 we start the class again na. Okay, 7:40 we start the class. Till then you can take a small break. It's already 2.5 hours. We are about to complete the heat transfer part, and then thermal expansion, then calorimetry we will cover. You can take a small break. Okay. Hello. Hello guys, I'm back again, and heat transfer we are about to complete. There is only one concept left in it, and that is the Wien's displacement law. This is the last concept of the heat transfer. After this, thermal expansion and the calorimetry, two topics are remaining. Okay, so should we start the session? So Wien's displacement law. We are we are talking about the radiation by the bodies. It could be a black body, it could be a normal body. So we analyzed the intensity of the radiation emitted by a black body. We analyzed the intensity of the radiation emitted by a black body corresponding to the different wavelength present in the radiation. He draw like using the what does Wien do? He analyzed the intensity of radiation corresponding to their wavelength. So there is a black body. 1 minute, everything has changed. So there is a black body at temperature T. This is radiating energy. We analyzed the intensity corresponding to different wavelengths. So lambda on this axis, intensity on this axis. The curve was like this. So at 500 Kelvin, you are getting this curve, and 1000 Kelvin, you are getting this curve. This intensity is maximum at lambda m1, and the intensity is maximum at lambda m2. So when you increase the temperature, the wavelength corresponding to which maximum intensity is occurring will decrease. This was the observation of the Wien. So Wien's displacement, with the help of the Wien's displacement curve, we can say when the temperature of the body is increased, it will radiate more energy on the lower wavelength side. So the maximum intensity corresponding to the wavelength, that wavelength will decrease if you increase the temperature. So he deduced a formula as well. Lambda m into T is equal to Wien's constant, and the value of Wien's constant is equal to 2.88 into 10 raised to the power minus 3 meter Kelvin. This lambda m is the wavelength. Lambda m is the wavelength corresponding to maximum intensity. So wavelength corresponding to maximum intensity is lambda m, then lambda m into temperature in Kelvin is equal to Wien's constant, and that is 2.88 into 10 raised to minus 3 meter Kelvin. This is a very simple formula. So whenever you see in a question wavelength and temperature, you just think about this formula. So lambda m into temperature is equal to constant according to Wien's displacement law. So there is one question. The spectral emissive power of a black body at a temperature of 600 Kelvin is maximum at lambda m is equal to 5000 angstrom. If the temperature is increased by 10%, then the decrease in lambda m will be. So if you increase the temperature by 10%, you have to find the decrease in lambda m. So if you increase the temperature, lambda m will decrease, and temperature is increased by 10%. 10% is not a small. So initial temperature T initial into lambda m initial is equal to T final into lambda m final. So initial temperature is 6000 Kelvin. That into lambda m initial is equal to final temperature is increased by 10%. So 6000 ka 10% is 600. So it becomes 6600 into lambda m final. If you divide both, 1.1 lambda m final. So lambda m final becomes lambda m initial divided by 1.1. We can write 10 by 11, which is approximately equal to 0.9 lambda m initial. So lambda m final will become 0.9 lambda m initial. So what is the delta lambda m? And that comes out to be 0.1 lambda. Wait 1 minute now. Then the decrease in the lambda m will be ten lambda m initial divided by 11. That comes out to be 0.9 lambda m initial. So let's not write it like this. This is 10 lambda m initial divided by 11. Okay. So delta this will be equal to lambda m initial minus lambda m final. So lambda m is equal to 1 minus 10 divided by 11, and this comes out to be lambda m divided by 11. So this comes out to be lambda m divided by 11, which is approximately equal to 0.9 lambda m initial. So delta lambda m divided by lambda m initial is equal to delta m initial is equal to 0.9, and you multiply with this will be 0.09. So 0.09 multiplied by 100, it will be 9%. So decrease in the value of lambda m will be 9%. Okay. So decrease in the value of lambda m will be 9%. So the spectral emissive power of the black body is increased by 10%. Then the decrease in the lambda m will be 9%. This will be the answer. Thermal expansion of the solids and the liquids. This is the next topic in this series. So thermal expansion of the solids and liquid. So material expand on increasing their temperature. When you increase the temperature of the material, they expand. Why do they expand? When temperature is increased, the amplitude of the vibration of the molecules increases. So let's say molecules are oscillating at this distance like this. When you increase the temperature, their vibrational kinetic energy will increase. So now they start moving like this. So now the effective distance between their center will increase. Initially they were oscillating like this, so effective distance was like this. Now they are oscillating like this. Now their effective distance will increase. So when you increase the temperature, the amplitude of the vibration of the molecule increases, which result in the greater average separation between the molecules, and hence we can say on increasing the temperature, material expands. There is a one exception as well, water. Up to 4 degrees Celsius, that we will cover in later. Okay. So material expand on increasing their temperature. The temperature increases, amplitude of the vibration of the molecule increases, which result in the greater average separation between the molecules. There are some example of the thermal expansion. In thermometer, the reading we take using this concept only, at higher temperature, the mercury in that tube expands, and based on that we take the reading of the thermometer. So the concept of the thermometer is based on the thermal expansion. There is a between the rays of like, what do we call them? We call them patri in Hindi, na? So there is a gap between two patri. You understand it, no? Like this we call patri in Hindi. So they leave gap between two. Don't remember what we call it that in English. You have seen this kind of joints on the bridges, and they leave gap there also. So when if there is a bridge, they leave this gap so that in summer there is expansion. So this expansion will be adjusted in this gap. Otherwise, bridge will bend upward actually due to the expansion. So these are some example of the thermal expansion. There is problem with English as well. So let's talk about the linear expansion. So we are going to talk about the linear expansion. So suppose there is a thin rod of length L and temperature is T. We increase the temperature, we make it T plus delta T. We increase the temperature and make it T plus delta T. The length of rod becomes L plus delta L. The length of the rod becomes L plus delta L. So this increase in the length, is given by this increase in the length delta L is directly proportional to L. This increase in the length delta L is directly proportional to change in the temperature, which is the delta T. So when you increase the temperature of the rod of length L, that depends, the change in the length of the rod depends on the length, depends on the temperature, and it comes out to be delta L is equal to L alpha delta T. I'm feeling like I'm out of stock of English words. All the words, all the words I have already used. I'm out of stock. It's difficult to teach in English. Like for me actually, I am from Hindi medium. I'm from Hindi medium background. For me it is difficult. Still, I'm trying my best so that you understand it in a maximum possible way. Okay, not a problem. So even if a linear object will expand, if you increase the temperature, the length of the rod is L, temperature is T, you have raised the temperature by delta T, length becomes L plus delta L. That delta L depends on the length of the rod itself, delta L depends on the temperature change, delta L is equal to L alpha delta T, and this alpha is called the linear expansion coefficient of the temperature. Linear expansion coefficient of temperature. From here we can get alpha is equal to delta L divided by L into 1 upon delta T. So if delta T is equal to 1 unit, fractional change in the length is equal to alpha. So this is the definition of alpha. So alpha is called the linear expansion coefficient of the temperature, and alpha is equal to delta L upon L into 1 upon delta T. And for per unit temperature change, fractional change in the length is equal to alpha. Alpha is of order of 10 raised to the power minus 5 per degree Celsius. This is the order of alpha. So if you are changing temperature up to 100 degrees Celsius, then fractional change comes out to be order of 10 raised to the power minus ka 3 mm order. Okay, so L length rod is there, temperature is changed by T and delta T. The change in the length is this. Why this change in the length is directly proportional to length? So let's say there is a length L and there are total 1, 2, 3, 6 bonds are there, and if you take 2L length and there are 12 bonds, there are 12 bonds. If on increasing the temperature, one bond length increases by x, then change in length will be equal to 6x. Here there are 12 bonds because length is double. So change in length here will be 12x. So more is the length, more will be the change in the length. So that's why we said delta L is directly proportional to length and delta L is also directly proportional to temperature. So more you change the temperature, more will be the change in the length. Is this clear to everyone? Why we write delta L is directly proportional to L? Because more is the length, more will be the number of bonds and more will be the change in the length. Okay. So let's solve a question on this. A bar of iron is 10 centimeter at 20 degrees Celsius. At 90 degrees Celsius, it will be, so they are decreasing the temperature. From 20 degrees Celsius to 19 degrees Celsius, they are decreasing the temperature. Alpha is given as 11 into 10 raised to the power minus ka 6 per degree Celsius. Alpha is given as 11 into 10 raised to the power minus ka 6 per degree Celsius. Length is given as 10 centimeter. So change in length, it will decrease, obviously, because you are decreasing the temperature. So length will be shorter, and what will be the amount of that? That will be L alpha delta T. So L is 10 centimeter multiply by alpha, which is 11 into 10 raised to the power minus ka 6. Change in temperature is 1 degree Celsius. So delta L becomes 11 into 10 raised to the power minus ka 5 centimeter. So it will become 11 into 10 raised to the power minus ka 5 centimeter shorter. This will be the correct option. So directly formula based question can be asked on this part. So delta L is equal to L alpha, delta T is the change in the length of the rod when you change the temperature by delta T. There is a effect of temperature change on the metal scale. If you are taking any reading using the metal scale, the reading will be affected by the temperature change. Okay. So let's say there is an object. This length you have to measure using the metal scale. This is your scale. This is metal scale. And this is object which is to be measured. Okay. So object will also increase on increasing the temperature. So alpha of object is given. Alpha of the scale will be given. How do we take the reading? We coincide the end of this object with the 0 of the scale. There are division on the scale like this. So this length at the calibrated temperature, there is a temperature which is called the calibrated temperature. At which scale gives the correct reading. Or it is the scale gives the correct reading at the calibrated temperature, and that temperature is T naught. Let's say that object is measured using the scale at calibrated temperature T naught. This is 1 division, 2 division, 3 division, 4 division, 5, 6, 7, 8. So length is measured. Length of the object at calibrated temperature is equal to 8 division. If you call it 1 division is equal to 1 centimeter, then the object length is 8 centimeter. Okay. Now if we increase the temperature, there will be expansion of the object. Along with the expansion of the object, there will be expansion of the divisions as well. These division will also shift. So at any other temperature, the reading will be equal to, if we change the temperature, if we change the temperature, the reading will be equal to, reading is equal to L naught, which is the length of the object, 1 plus का alpha of the object into delta t divided by 1 plus का alpha of the object into delta t divided by 1 division 1 plus का alpha of the scale delta t. So reading of a scale is given by this formula. You can directly remember this formula. Reading of the scale is equal to L naught 1 plus का alpha of the object minus का alpha of the scale into delta t divided by 1 division. This is the reading at any temperature T by the scale. This formula, I'm not going into the derivation of this formula. This formula will always help you in finding the answer of question related to the expansion of the scale. So if there is no expansion of the object, if let's say object is not expanding, object is made of wood and the scale is made of the metal, so object alpha will be equal to 0. Now length at higher temperature, the reading will be less than the actual length. The reading will be less than the actual length. So let's say I just ask you a question. I did not plan it earlier. A scale gives correct reading at 20 degrees Celsius. Scale gives correct reading at 20 degrees Celsius if it measure wooden rod at 50 degrees Celsius and reading is 100 centimeter. Find the actual, what will be the actual length? Length of a rod is, it will be greater than 100 centimeter, less than 100 centimeter, equal to 100 centimeter, or cannot say. What will be the correct answer of this? A scale which gives the correct reading at 20 degrees Celsius and you are measuring the length of a wooden rod at 50 degrees Celsius. You are measuring the length at a higher temperature and it is giving the reading equal to 100 centimeter. At 50 degrees Celsius, it is giving reading 100 centimeter. So what is the actual length of the rod? Is it greater than the 100 centimeter, less than the 100 centimeter, or equal to 100 centimeter? Actual length of the rod. So the rod, wooden rod will not expand. Okay, keep this thing in mind. Wooden rod will not expand. You have to find the length, actual length of the rod. What will be the actual length of the rod? Will it be greater than the 100 centimeter, less than the 100 centimeter, or equal to 100 centimeter? So you have this formula in front of you. Okay, use this formula. This is called the actual length. This is called the actual length. Reading, they are giving 100 centimeter. Reading is 100 centimeter. So this is 100 centimeter. They are asking this. Alpha of object is 0. So this is 1 minus ka alpha of the scale into delta t. Alpha of the scale into delta t. So this term is less. You multiply that with L naught you are getting 100. L0 will be greater than 100. L0 will be greater than 100. So the actual length of the rod is greater than 100. Okay. Let's say this division is 100. Okay. Suppose this rod is of 101 centimeter. 101 centimeter. So at 20 degrees Celsius, 101 centimeter division will be here. When you increase the temperature, that 101 centimeter will move and 100 centimeter will come to this end. At 50 degrees Celsius, your reading is 100 centimeter. That means the actual length of the rod is more than 100 centimeter. Because you increase the temperature, the divisions of the scale has increased. So at higher temperature, it is giving 100. That means the actual length was more than 100. After expansion, the 100th division is equal to the length of the rod. The rod length will be greater than 100. Okay? Clear? Is this clear? This formula will help. The reading at 50 degrees Celsius, 100, L0 we have to find. This formula will always help. That's why I have written this formula. I know I don't want you to take into the derivation part. Otherwise, it will be difficult for you to understand. So this formula will always help you in this kind of question. Whenever you are talking about the scale related question, just use this formula. This will be very helpful. There is one more concept, time lost or gained by the pendulum clock. Have you ever seen the question, this kind of questions? There is a simple pendulum clock. You increase the temperature, will it lose the time or gain the time? This kind of question. Okay. So time period of the simple pendulum clock, time period of simple pendulum clock. Time period of the simple pendulum clock is 2 pi root over L divided by G. Okay, time period of the simple pendulum clock is 2 pi root over L divided by G. Changing temperature changes length of the simple pendulum. Hence, time period changes. Time period of the simple pendulum will also change. Time period changes. So what is the relation between time period and the time? See, there is a second hand of the clock. It just wait for the pendulum to move from one extreme position to the other extreme position. When this pendulum move from this bob move from this extreme position to this extreme position, it just read 1 second. It will read 1 second. When again this move from this extreme position to the other extreme position, it will move 1 more second. And what is that? This time interval? This is equal to T by 2. So half of the time period is the time interval from one extreme position to the other extreme position. And that time, that is the indication when this second hand of the clock is moved by 1 second. Okay, that is the time when the second hand of the clock will move by 1 second. So if it start taking more time from here to here, it will click 1 second in a more than 1 second time. So we say clock is slow down, like the clock is slow because let's say now simple pendulum time period is increased. If simple pendulum time period is increased and the simple pendulum is taking 1.1 second from one extreme position to other extreme position. When this pendulum reaches from this extreme to that extreme, then only it moves 1 second further. Okay. Now it is taking 1.1 second from this extreme to the other extreme position. The clock will read 1.1 second is equal to 1 second because it does not have anything to do with the with this second hand. It only reads 1 second when the Bob leave this extreme position and reaches the other extreme position. It does not know what is that 1 second time. This clock does not know. It simply says whenever pendulum reaches from this extreme to the other extreme position, it will be reading 1 second. If it is taking more time, then we will say clock is slow, and if the time period is decreased, the clock becomes faster and it will gain the time. And the time period is increased, it will be slow and it will lose the time. So you can directly write it. Time period increases, if time period increases, clock will become slow. It loses time. Okay, it loses time. Time period decreases, clock becomes faster. It gains the time. It will gain time. Okay. So when time period will increase, when length will increase. So at higher temperature, T0 is the calibrated time. So at this temperature, it will give the correct reading. So if T is greater than T0, if the clock is operating at a higher temperature, it will slow down. And loses time. Okay. And what is the time lost or gained? Time lost or gained is equal to 1/2 alpha delta t into time. This is the time lost or gained by a clock in any time t. Okay. 1/2 alpha delta theta into time. So this is the time lost or gained in any time. So this is the direct formula. Just remember this formula. 1/2 alpha delta theta, 1/2 delta alpha delta t into time is the delta theta you write for the temperature. Okay. For the temperature we are writing delta theta, and this is the time lost or gained by the clock. So there is a question. A pendulum clock has an iron pendulum of 1 meter long. Alpha of iron is 10 raised to the power -5. If the temperature is raised by 10 degrees Celsius, what will happen to the clock? If the temperature is increased by 10 degrees Celsius, now you are operating at a higher temperature. What will happen? It will lose the time. The temperature has increased. Time period, no. 1 minute. Time period increased, clock will become slow because at higher time period it will read less time. Okay. So time period will increase, clock will slow down, it will lose the time. So either A option will be correct or B option will be correct. So in a day, what will be the time lost or gained by the clock? So delta T, it will be lost because you are operating it at a higher temperature. The time period will be more, it will slow down. Delta T will be equal to 1/2 alpha delta theta into, in a day there are 24 hours and in an hour there are 3600 seconds. So from here we get 1/2 alpha is equal to 10 raised to the power -5. Delta theta is 10 degrees Celsius into 24 into 3600, 123. Okay. This will become 12 and 72, 32, 36 और 47. 4.32 second it will lose per day. So this will be the answer of this question. It will lose 4.32 seconds per day. Will you remember this formula? Time lost or gained, and will you be able to identify that it will lose or gain the time? Is this clear? That's correct, na? To lose. Okay. Let's move to the area expansion. Similar to the linear expansion, let's say there is a sheet of B naught width, L naught length. There are molecules arranged in this direction, molecules arranged in this direction. This length is L naught, this length is B naught. So its initial area was A naught, which is equal to L naught into B naught. But when you increase the temperature, this length will change. There are molecules oscillating like this. Their separation will increase. So there will be expansion in this dimension. L will become L naught alpha x delta t. So let's call this direction x direction. In this direction, alpha is alpha x. This direction is the y direction. So B will become, on increasing temperature, B becomes B naught alpha y into delta t. Area will become L into B, which is L naught into B naught 1 plus alpha x delta t into 1 plus alpha y delta t. When you multiply both of them, so area, new area becomes A naught, L naught into B naught is A naught, 1 plus alpha x plus alpha y into delta t. There was one more term which we can ignore because this term is already small, this term is already small, and the multiplication of these two will be very small. So A is equal to A naught 1 plus beta delta t. So beta is equal to alpha x plus alpha y. If alpha x is equal to alpha y is equal to alpha, then beta is equal to 2 alpha. Then beta is equal to 2 alpha. And in that case, A becomes A naught 1 plus 2 alpha delta t. Beta is called the area expansion coefficient. Area expansion coefficient of temperature. So area expansion coefficient of temperature is beta, which is equal to twice of alpha. So area will also expand. This is the area expansion of the when you increase the temperature. A thin copper wire of the length L increases length by 1% when it is heated from 0 degrees Celsius to 100 degrees Celsius. If a thin होगा, copper plate of area 2L into L is heated from 0 degrees Celsius to 100 degrees Celsius, the percentage increase in the area will be. So they are saying the percentage change in the length delta L upon L is equal to alpha delta t, and they multiply this with 100. So multiply this with 100 and that comes out to be 1%. Okay. Now they are saying delta A upon A, that comes out to be beta delta t. Multiply it with 100. Multiply it with 100. So beta delta t will be, beta is 2 times alpha delta t into 100. It will be equal to 2%. So percentage change in the area will be 2%. You might get confused, sir. The area is double, but they are talking about the percentage change. So percentage change will be beta delta t into 100, and beta is twice of alpha. So 2% will be the change in the area, and you get the answer. That is, second option is the correct option. So area expansion is done like this. For what happened, like, is this not in the syllabus of the NEET? Let me check once. give me 1 minute, na. Thermodynamics, properties of the solid and liquid. So there is heat is there, temperature, thermal expansion is there. Thermal expansion is there. Specific heat, calorimetry, conduction, convection and radiation, they all are there. Who was saying that this is removed from the syllabus? In radiation, all the concept of which I have taught you today are covered. They don't have to separately write it, like Newton's law of cooling and all are already the part of the radiation. Okay, so question number, this was the question number 11. Let's talk about the volume expansion. Expansion part is there in the syllabus, so don't get confused with that. Now we are talking about the three-dimensional object. So there is this object, three-dimensional object. Let's say this is H0, this is L0, and this is B0. So volume of this is equal to L0, H0, B0. Okay. All the three dimension will increase if we increase the temperature. So new volume becomes L0 1 plus alpha in x direction delta T. New height becomes 1 plus alpha in y direction into delta T. And new width will become B0 1 plus alpha in z direction delta T. So volume is equal to L0 B0 into H0 1 plus का alpha x alpha y alpha z delta T. So volume is equal to V0 1 plus का, we call it gamma delta T, and the value of gamma is alpha x plus alpha y plus alpha z. If they all are equal, alpha x is equal to alpha y is equal to alpha z, then value of gamma is 3 alpha. So volume becomes V equal to V0 1 plus 3 alpha delta T, and delta V is equal to V0 gamma delta T. Okay, so this is the volume expansion coefficient, and volume will change just like length, but the expansion coefficient in case of volume will be 3 times. So 3 alpha is the expansion coefficient of the volume. Remember one thing, every dimension will increase. So there I could not add the question. So let's say there is a sheet and there are 2 holes in it. Okay, there are 2 holes in the sheet. Radius of this is A, radius of this is B, and the gap between both the hole is T. On increasing the temperature, what will happen to A, B and T? On increasing the temperature, what happen to A, B and T? Can you comment on this? So if you increase the temperature, what will happen to A, B and T? Will the radius A will increase, B will increase or decrease, T will increase or decrease? What will happen to all the three? What will be the what will happen to A, B and T? A, B and T, what will happen? A, B and T, what happens to A, B and T? So the answer of this question is they all will increase. Even the free part, if there is a cavity, or say there is a container, so there is a hollow part in that container, when you increase the temperature, everything will increase. So A will increase A, B and T all will increase. Even this separation will also increase. This sheet will increase, the radius will increase, and this gap will also increase. All of them will increase. All of them will increase. All of them will increase when you increase the temperature. This was the volume expansion. Temperature effect on the density. Effect of temperature on the density. So, if you have a substance of mass m, mass does not depend on temperature. Does not depend on temperature. Mass does not depend on the temperature. It is independent of the temperature. Mass is given by rho naught into V naught. So suppose density is rho naught at reference temperature and volume is V naught. If you change the temperature, volume will change, hence density will change because the product is constant. So rho into V, which is mass, is equal to V is the volume actually, not this V. So V is the volume, is equal to rho naught into V naught. So rho becomes rho naught into V naught divided by volume, which is V naught 1 plus ka gamma delta T. So density becomes rho naught divided by 1 plus ka gamma delta T. On increasing the temperature, density decreases. There is one exception. I was talking about that only, So on increasing the temperature, density decreases, but there is an exception. Water. Till 4 degrees Celsius, density of the water first increases and then decreases. This is just an exception, you have to keep that in mind. Okay, up to 4 degrees Celsius, the density of the water increases and then decreases. Otherwise, for all other substances, density decreases with the increase in the temperature. And what is the expression for that? So density can be written like rho equal to rho naught divided by 1 plus ka gamma delta T. This is the effect of the temperature on the density. Temperature effect on the floating objects. I have covered most of the concepts, like any possible question that can be asked from you is covered in these notes. The speed is a little bit fast, and that is actually required as well. I hope you all are able to understand that, because there is a time problem as well. So when there is an object floating like this volume is called the V submerged, and total volume is V naught. Total volume is V naught. So if this object is floating, for a floating object, V submerged divided by V naught, this is called the fraction of the volume submerged. Fraction of volume submerged. This is called the fraction of the volume submerged. V submerged divided by V naught is equal to rho of object divided by rho of liquid. Object density divided by liquid density is the fraction of the volume submerged. And sometimes questions are asked about this. So what will be the effect if we increase the temperature? So if we increase the temperature, this object density will become 1 plus ka gamma of the object delta T, and this liquid density will become 1 plus ka gamma of liquid into delta T. So when you solve these two this becomes rho naught divided by rho of liquid 1 plus का gamma of liquid minus का gamma of object into delta T. So if gamma of liquid is greater than gamma of object, if gamma of liquid is greater than gamma of object, fraction new is greater than fraction old, and if gamma of liquid is less than gamma of object, fraction new will be less than old fraction of the volume submerged. So fraction of the volume submerged we will get from this formula. Fraction of the volume submerged is equal to fraction 1 plus gamma of liquid minus gamma of object into delta T. The temperature effect on the floating objects is this. There's the liquid expansion as well. So let's say this is the volume V naught. When you increase the temperature, everything will increase, like container will also expand, its height will increase, its base will increase. This will happen. The new container will be like this. So the same volume of the liquid will become V naught 1 plus ka gamma of the liquid into delta T. Okay. V naught 1 plus ka gamma liquid into delta T. Let's say the initial height in the container was equal to H. Initially the container was filled up to height H, and this base area was equal to capital A. This was the base area. So volume of the liquid was equal to A into capital H 1 plus ka gamma liquid into delta T. Now the base area has changed. Let's call it A naught, H naught. This was A naught, H naught. Now area has changed. Now it has become A naught 1 plus ka 2 times alpha of the container into delta T. Now you pour that same volume into the new container. So new area, which is A naught 1 plus ka 2 alpha of the container into delta T, this into new height will be equal to the total volume of the liquid, which is A naught into H naught 1 plus ka gamma of the liquid into delta T. The new height comes out to be, I think this is not in your syllabus, na? We can skip this part. The new height comes out to be H naught 1 plus ka gamma of liquid minus ka 2 alpha of the container into delta T. Only just if you want to keep, you want to remember this formula, then remember this. The new height in the container will become this. But I think this is not in your syllabus actually. This is not in your syllabus. I hope not in your syllabus. It is a part of the JEE. I should not have covered it. Otherwise, liquid expansion questions, we don't have to go to this much depth. Okay, we can skip this part. No, this question is not required. I have already solved that question. So we are talking about the concept of the thermometer. This is important. So concept of the thermometer concept. Here you can see there is a mercury filled in this tube. There are marking. There are two different scales used. One is a Fahrenheit scale, other is a some degree Celsius scale. I don't know this is correct or not. Okay, so this is degree Celsius and that is Fahrenheit. So what we do, in this tube there is mercury. When you increase the temperature, mercury expands and it rises, its level rises, and based on that we take the reading of the temperature. So we have an ice point temperature when thermometer is kept in ice water mixture. There is a steam point when thermometer is kept in boiling water. So for any thermometer, T minus T ice divided by T steam minus T ice is constant. For any thermometer, T minus T ice divided by T steam minus ka T ice is constant. So this is the concept of the thermometer. And for degree Celsius, ice point is 0 degree Celsius and steam point is the 100 degree Celsius. For Fahrenheit, ice point is 32 degree Celsius, 32 Fahrenheit, and the steam point is 212 Fahrenheit. We take 180 division on the Fahrenheit scale, or and on degree Celsius scale we take 100 divisions. So there is a question on that. In a temperature scale called Z, the boiling point of the water is at 65 Z and the freezing point is at minus ka 14 Z. Then the temperature T, which is minus ka 98 Z, correspond to the Fahrenheit scale too. So there is a new scale whose steam point is 65 Z and ice point is minus ka 14 Z. You have to convert this reading into Fahrenheit reading. So T minus ka T ice divided by T steam minus ka T ice is equal to new scale temperature minus ka T ice of that scale, T steam of that scale minus ka T ice of that scale. So temperature on this scale is minus ka 98 minus ice point is minus ka 14 divided by steam point is 65 minus ka 14 is equal to temperature at Fahrenheit minus ka ice point for Fahrenheit is 32. This is 212 minus ka 32. So this comes out to be 84 minus 84 divided by, this comes out to be 79 is equal to T minus ka 32 divided by 180. How do we solve this? (65 Z and 14). Very bad calculation. Minus का 98 Z minus का 98 minus का minus 14. अरे यार, how do I solve this question? This is very bad calculation. It's 59 something, 159. Thank you for saving me. So T equal to, they are saying minus ka 159 Fahrenheit. Okay, thank you. Okay. So today we will stop here. Calorimetry I'll teach in some other class. These two topics, like with some small topic I'll teach you calorimetry, okay? So heat transfer and the thermal expansion, they are very big topics actually. In class I take 3 hours, I teach heat transfer and thermal expansion for 3 hours. So 6 hours, in 6 hours I complete these two topics. So with that thing in mind, I have covered these topics in less than 4 hours. So I understand the lecture was a little bit faster than usual, but I hope you understood the things which I have covered. This level of teaching, this level of concept clearance is required. If you are able to understand all the concepts, these are the concepts on which the questions can be asked in the exam. So like you should compare the content which you are already getting, that is that content up to the level of the NEET, which level is required actually for you. Okay students, so we end the class here and we will meet in the next class. I'll be most probably taking the topic from the starting, because in the starting we have covered till vectors, and I think we should start with the kinematics part. So kinematics part I'll cover in the next class, and we are done for today. Okay, thank you, take care. So answer is minus 191. So please calculate this and do the calculation part. The concept is this. Concept is this. You have to do the calculation part. So out of 1 or 2, there will be one option. I did not solve the this thing. Like calculation part you have to do. I'm very tired today. Like that's why I'm not teaching you the calorimetry part. Calorimetry part I'll teach with some other small topic. Okay. Okay. Bye. Take care. Thank you.